For decades, the story of our universe followed a strict, reliable script. The cosmos was 13.8 billion years old, expanding at a uniform rate, and cooling slowly enough to allow gas clouds to gradually collapse into the first stars and galaxies. That script originated with the math of general relativity. It provided a balanced, predictable equation for reality that physicists tested and relied upon for a century. A critical pillar of that math is isotropy, the requirement that the universe looks the same in every direction. In this model, space has no preferred center and no specific orientation. Any random patch of sky should look like any other. For a long time, our equations and our observations were in perfect sync, creating a period of total scientific consensus. Then we launched James Webb. Positioned 1,000,000 miles from Earth, this infrared instrument was designed to look back at the earliest moments of light and confirm our exact models of how the first structures formed. When the first deep field images arrived at the control center, scientists were not looking at a quiet, cooling universe. Where the textbooks predicted empty space, they found hundreds of sharp, highly detailed, and mature galaxies. The presence of these objects creates a direct conflict with our existing math. The universe we are seeing is incompatible with our established rules. The first conflict is a matter of time. Webb found massive, organized galaxies existing just 500 million years after the Big Bang, long before the standard timeline says they should have had enough matter to assemble. Tucked inside these early galaxies are what researchers call little red dots, massive black holes feeding on gas at rates that ignore the traditional physical speed limits of accretion. Under standard physics, a supermassive black hole grows from the collapsed core of a dying star. But that process is slow, requiring billions of years to reach the masses Webb is seeing in the very first chapter of cosmic history. To explain this, physicists are revisiting a theory proposed by Stephen Hawking in the 1970s. He suggested the existence of primordial black holes, objects born not from stars, but from the raw, high-pressure energy of the Big Bang itself. This suggests the early universe wasn't a slow gathering of gas. It was a place that possessed massive cosmic seeds from its first second of existence. This timeline visualizes the Hubble tension. Measurements of the early universe predict space expands at 67.4 kilometers per second, but observations of our local universe show it moving at 73. That 9% gap creates a break in our calculations of the age of the universe. Across 13 billion years, that discrepancy places galaxies in locations that the math cannot account for. For years, researchers hoped this was a measurement error. But Nobel laureate Adam Rees used Webb's infrared eyes to cross-check these distances, proving that the discrepancy is real and the tension is here to stay. We are also seeing a break in how we understand dark matter. Standard cold dark matter is thought to be clumpy, pulling gas into roughly spherical, round galaxies. Instead, Webb sees elongated, cigar-shaped galaxies. These shapes suggest the dark matter scaffolding isn't clumpy, but rather wave-like, ultralight particles behaving like a quantum wave that stretches light-years across. This change in shape suggests the invisible matter that makes up the majority of our universe is operating under quantum rules we never built into our models. This leads to the most difficult anomaly, the failure of isotropy. Remember, the universe is supposed to be random, with no specific orientation. In a sample of 263 early spiral galaxies, 2/3 were found to be spinning in the exact same clockwise direction. In a random universe, this is as unlikely as a coin landing on heads 175 times in a row. This pattern suggests the universe has a preferred axis, a built-in memory of a specific direction that was present from the beginning. In general relativity, a rotation requires an external frame of reference, something outside to spin against. This suggests our universe inherited its spin by being born inside a larger, rotating parent structure. This is the foundation of black hole cosmology. If our universe formed inside a black hole in a different cosmos, it would inherit that parent's rotation. Our galaxies would spin clockwise because the parent black hole was doing the same. Skeptics of this new data have proposed many ways out. Perhaps the rotation is an illusion caused by the Milky Way's own motion. or the mature galaxies are just a trick of cosmic dust. But Webb was built specifically to bypass the limitations of older telescopes. Its infrared precision has allowed researchers to cross-check every potential error, confirming that these anomalies are not artifacts of the instrument. The data is clear. The instruments are working perfectly, which means it is our underlying framework that needs to be rebuilt. This isn't a crisis of failure, but a renaissance of discovery. We are in a period where old certainties are being replaced by data that was previously impossible to collect. We are now forced to account for a cosmos potentially anchored by primordial seeds, held together by quantum waves, and possessing a physical heritage from a parent structure. James Webb is providing the high-definition data needed to redraw our maps from scratch. The data is final, even if the new story is only on its first page.